performance in neural circuits.
Cool. Thanks for having me here. Nice to invite me. Unfortunately, so I came to Montreal for a holiday. It's a great city, but I got a fever as soon as I came. I'm still running the temperature, so if my brain is not switched on, apologies in advance. Okay, so this is work with Adriana, a new PhD student in our group, and Timothy O'Leary, who's my PI. I think hopefully it goes without saying, but please feel free to ask questions during the talk. If you don't understand something, that's probably my fault, not yours. So yeah, on that note, let's get started. So I'm going to start with a simple observation in a very simple scenario. So I'm doing online supervised learning, and the simplest neural network I can think of, and the simplest task I can think of. So I've got a feed-forward neural network, a couple of hidden layers, sigmoidal nonlinearities, generic tasks. So what I do is I make a teacher network with exactly the same architecture as the student. I randomly fix the weight, and then it's the task of the student to learn to do. This is just so that I can have a kind of agnostic task. It's the easiest one to think of. I put Gaussian inputs through both, and then I do supervised learning. The student sees the teacher labels, the teacher-generated labels, and it learns. Very simple. What happens is we increase network size of the student while keeping the teacher constant. In the regime where we have noisy weight updates, so we're not just doing pure propagation, we're corrupting our gradient with some noise, and a fixed plasticity magnitude. So really the point of this is that there's a lower bound on the degree of plasticity. I'm in neuroscience, so I'm interested in brain relevant context. And the brain doesn't freeze ever. But I don't really care what the actual plasticity magnitude is. But what happens is, as I get iteratively larger networks, student networks, the steady state error gets better. And I get faster learning, as you can see on the left. So here's some time courses of error over time. And here's the steady state error for a couple of repeats. Why is this strange? Well, the teacher had the same architecture as the smallest student. So technically, the smallest student could learn to zero error perfectly. There exists some weight states of the smallest student that could perfectly recreate the teacher. So something is going on here. Somehow the bigger networks are more robust to the noise in the weight updates. So why is this interesting? Well, when I started my postdoc in neuroscience, one of the first things I learned about, for instance, were place cells. Wait, are people here familiar with some degree of neuroscience, or are you pure AI people?
Not really.
Okay, okay. Basically, a lot of neuroscience, what happens is you make an animal like a monkey or a mouse for a task, simultaneously image the neurons. And it turns out that you can decode what the organism is doing, where it is in the maze, its spatial location, just by a statistical regression on the neural activities. Now, the interesting thing here is that you're imaging like 100 neurons. You put your microscope in somewhere random out of millions. So what that's saying is there's a lot of redundancy in the neural representation.
So those are the place cells?
Place cells was a particular example of that. Okay. Place cells are cells which basically represent locations. So if you put a mouse in a maze or any animal, place cells fire where one place cell will fire when I'm at this point in the maze, and another place cell will fire when I'm at this point in the maze, which means that just by looking at the neural activity, I can infer where the mouse is. That was just an example, but that's also.
Oh, sorry, you finished.
Sorry?
It's just for the next question. I didn't mean to interrupt.
Okay, sure. But the point is that you can actually decode the location of a mouse in the maze by looking at 100 random place cells where your microscope is, whereas there's millions of place cells, tens of millions. So there's a lot of redundancy.
And when you said statistical regression, did you mean simple linear regression, or does it have to be something than that?
Usually what they use are generalized linear models, I think. You can use linear regressions. I've seen that where linear regressions. Essentially, for place cells in particular, you kind of have a bump function. So literally, like this place cell fires with the highest firing rate when I'm here, and it's got a Gaussian firing rate around here. So it's a bit lower here, and it's pretty much zero when I'm here. Yeah. But the point is, the fundamental point I wanted to make is there's a huge amount of apparent redundancy in the brain. And maybe there's some similar reason from the observation I gave just before, where larger networks with kind of more neurons than need to be somehow deal better with noise. And another interesting thing about this is it's saying that, well, we know bigger is better for neural networks in a sense. And normally we think about the reason for that being that bigger networks have greater model complexity. There's a larger space of input-output mappings that a larger neural network can realize. But maybe there's something else going on here. Well, there has to be something else going on here, because even the smallest network that I chose could actually learn to zero error in theory, or there existed some way to which that could happen. Okay, so I'm going to think about all the things. First, I'm planning action for talks as follows. So the first part, I'm going to think about synaptic plasticity in the brain, which is the adaptive mechanism by which the brain learns, or at least one of them, a major one. And I'm going to just quickly go over all the annoying things that happen in the brain that mean that inevitably you can't have a very targeted weight update, you might say, in the brain. There's going to be all sorts of stuff corrupting it, which means that learning is going to be very noisy by definition in the brain. And I'm going to turn that into a neat formula that kind of doesn't impose a particular learning rule, but imposes arbitrary proportions of good plasticity to bad plasticity. That's the first part. Then I'm going to look at how the bad bits affect learning rate. And I'm going to show that that depends on the geometry of the error surface. So I'm going to build a geometrical concept which essentially is going to tell us how much weight changes in arbitrary directions are going to hurt learning. And finally, I'm going to think about what happens when I change network architecture. So if I have a particular state of a neural network, and I transport it via a function to an equivalent state of a neural network with different architecture, same input-output properties, the local geometry of the error surface, the loss function, is going to change. And I'm going to show that actually that change can essentially make the image, the neural network in the image of this mapping, more robust to bad plasticity. So essentially you can look at mappings. By changing neural network architectures, you can make neural networks more robust to arbitrary plasticity and have faster learning rates in a very noise-corrupted learning regime. Cool. So I'm going to look at a general online learning scenario. This could be in AI or neuroscience, really. I've got a network with some weight vector, W, depends on which changes over time, continuous time. The network performs some task, but it doesn't do it perfectly, so there's some error. The error is fed back and somehow updates the weights via some learning rule. I'm going to try and keep the whole thing agnostic to a particular choice of learning rule. There's a huge body of literature trying to work out what learning rules are used in the brain. But honestly, we don't really know yet. It's an unsolved question. Cool. So just by definition, what is learning? Well, it's error decreasing over time, right? So if I take some time interval t, error decreases, which means that my loss function, which I'm going to call f, is getting smaller. Fine. Geometrically, I'm going to use this analogy a lot. I can think of my loss function as a landscape. I can think of, so in this case, I have two synaptic weights. Obviously, there'd be millions in real life. And the higher I am on this landscape, the worse my error is. What I'm trying to do is go downhill and get as low as I can. That's the geometric analogy. So obviously, if I need to get to the bottom, on average, I need to be going downhill. My direction of weight change is going to have to anti-correlate with the gradient of average. And just by the fundamental theorem of calculus, that's just a mathematical representation of that statement. So my direction of weight change is a time derivative, and it's going to have to anti-correlate with this gradient. So overall, the integrand is negative on most points in time in expectation. Cool. So those requirements are generic to learning, whether biological together. But what makes biological learning particularly hard? First of all, suppose I'm learning a tennis serve or something. I have very incomplete sensory feedback. I don't have enough information on what I did to even if I had the perfect learning rule to find the exact direction and weight space in which I should move to optimally change my error function. Maybe I just did one tennis serve, whereas I need to be looking at the whole space of tennis serves I did, you know? I have bad sensory feedback. And then my learning rule itself is probably going to have some systematic error. It's not necessarily that I can implement perfect adigrad or whatever in the brain. What does this mean geometrically? Well, the actual descent direction I'm going to take is not going to correlate completely with the optimal. Might in fact correlate quite poorly. Next, synapses in the brain are actually intrinsically unreliable. They're tiny molecular machines and they're subject to molecular noise. They have Brownian fluctuations. If the synapse is at a particular strength, it doesn't necessarily stay there forever. And second, actually, there's other stuff going on in the brain. There's various plasticity mechanisms, homeostatic plasticity mechanisms, learning other tasks. If you think of a particular task in the brain and you think of some synapses involved in the task, it's not that those synapses are only utilized to improve at that task, right? So there's other stuff going on in the brain. So I'm kind of trying to learn while I'm also going. And then there's time delays at every stage of this feedback loop, right? Large time delays potentially. It's going to take time for sensory information to be integrated into particular plasticity mechanisms and for those plasticity mechanisms to be affected. It's doing a task. I might be doing a task once in a while, and it might take time to do it. So maybe I pick a good direction of descent, but I move over the Earth's surface and I'm going up. So there's all these issues that make biological learning very hard. Now, in order to think about this, to represent this mathematically, what I really want is to have some kind of discrete representation of the weight updates, but synapses are moving continuously in time. So what I'm going to do is I'm going to think about a time interval that's smaller than the time delay or the temporal sparsity of the task. So on this interval in time between 0 and capital T, I'm going to say that no information on the task that it was gained after time 0 is available. So up to time T, I only know stuff about from time 0. Okay, and there's always going to be such a T just because it plays in that loop that is. Yeah. Now what I'm going to try and do is decompose this movement into a task-relevant portion and a task-irrelevant portion. And there's not a unique way to do this. I'm just going to do a way that, but what I'm going to say is I'm going to define task-irrelevant plasticity as any plasticity mechanism, anything that's moving the weights of the network in a way that has no information on the task. Suppose I gave you a network with a particular weight vector, and I said, you're trying to learn a task, but I didn't tell you what the task was. Choose a weight update. Of course, your weight update is going to be nonsense, because you don't know what the task is. In particular, in expectation, the weight update you choose would be orthogonal to the gradient. So if I take a random vector, on average, it's going to have 0 correlation gradient, because I'm as likely to be positive as it is to be negative. Minus n, or if I flip the sign. If I look at the second derivative matrix, I have a second derivative matrix. I'm going to call it the Hessian for the remainder of the talk. That has eigenvectors. And because I have no information on the task, I'd imagine that my weight up n, which has information on the task, is going to unbiasedly project onto the different eigenvectors. It's not like I'm going to systematically bias myself towards a large eigenvector or a small eigenvector. In expectation again. Okay?
What would be the weight update in task-relevant classes? What would be the error function?
So I'm always calling the error function f. I haven't got to task-relevant class yet. Yeah, I'll get to that in the next slide. But I'm just saying for an arbitrary error function. But yeah, the next thing is task relevant plasticity. And that depends on the order of the learning rule, actually. Suppose I had a first order learning rule. Are you familiar with that terminology? So one where I'm not computing any information curvature, I'm just computing information with gradient. So you could say that propagation is the stereotypical example of a first order. In that case, task relevant plasticity, I'm just trying to approximate the gradient. So the task relevant plasticity would be how much I projected onto the gradient. And in fact, my total rate update would be some amount of gradient plus this n, which has these zero correlations. By the second order learning rule, it would be different. My optimal weight update, if I knew exactly the gradient and the Hessian, would be minimizing, finding the optimal direction given both the curvature and the gradient. Okay, so for clarity, just to make the maths easy for the rest of the talk, I'm going to assume that I'm only dealing with first order learning rules. It's not that the mathematical machinery can't generalize the second order or higher order learning rules, but it makes things cumbersome. So I'm going to think about, on this time interval, my weight update as being a combination of gradient information and this task irrelevant plasticity term. Yeah. So, yeah. Okay. So now I can make an interpolated plasticity direction. You think of this as a kind of approximate derivative, although of course this time interval may not be present. So this is just, the average direction I'm going in over this time interval. And this is going to be important for the rest of the talk. So right now, this interpolated direction is a combination of gradient and task irrelevant plasticity. And I'm going to break this task relevant plasticity down further subsequently. So first, let's think about how does this task irrelevant plasticity term change as I increase the time interval? What if I doubled this time interval I'm thinking about? Well, there's extremal cases. Suppose this task irrelevant plasticity was arising from something like a Brownian motion, a completely undirected process. In that case, the magnitude of task irrelevant plasticity, so how far it moved me, is going to scale with root time. What's the other extremal case? Suppose it's taking me in a V-line in one straight direction. In that case, it's going to be linear in time. That would be true if, for instance, I had a systematic gradient approximation error. So this was due to some error in the learning rule. More likely, it's going to be somewhere in between these two exponents, t to the half and t. Right. Next, what about how does it scale with network size? But again, if I had a Brownian motion, suppose the synapse was subject to a Brownian motion, which is in fact the case, then the total magnitude of plasticity is going to scale with root n, where n is the number of synapses. On the other hand, if it was a systematic gradient approximation error, then it would only scale with how much my learning rate is essentially in the direction of the gradient. So it could be that I can only update my weights in a way that's 10% gradient and 90% noise. So how big that 90% noise is depends on how big the gradient is. So these are all extremal cases. But I'm going to put my overall expression for the interpolated synaptic update as a combination of these extremal cases. So I'm going to decompose this task relevant plasticity into two terms. This term is one that's linear in time and doesn't scale with the number of synapses. So that would be as, for instance, a systematic gradient approximation error. And the third term is what you get if you had a pure Brownian motion on the synapses. So it's scaling with root n and root t. Remember that this has the left-hand side here has a t in the denominator. Hi.
I didn't quite catch your last scaling.
This one.
Yeah.
Okay, basically, suppose my learning rule is fundamentally wrong in some sense, right? So I can only find a weight update which correlates, which has a given degree of correlation with my gradient. I can't get exactly the gradient. Let's say I can do 10% gradient and 90% nonsense. Yeah? If I increase the network size, I'm going to assume that that's the same. I'm assuming I have a learning rule whose fidelity in approximating the gradient is independent of network size. That's what I'm going to do for the rest of the talk. So actually, if you look at some kinds of learning rules, so some of the biologically plausible or semi-biologically plausible learning rules that people have been trying to construct in recent literature, that's not actually the case. But what you can do in those cases is just you can change this weight update, basically. You can turn this gamma 2 to have some independence if you needed to. Basically, yeah, so I am assuming that there's the fidelity of the learning rule is independent of network size, but it's not necessary for the rest of the maths. It's just because I need some formula for my weight update. And I could always change this. I could change the exponents here.
I guess so, like this, just like above where it's scaling with t, the systematic gradient, like it's sort of always pointing.
I mean, like it's always what, sorry?
Always pointing.
No. It could be pointing in different directions, right? So you're talking about the portion of task irrelevant, this task irrelevant plasticity. All I'm saying is that on average, it's uncorrelated with the gradient. There's a portion of my weight update that is the gradient, and there's a portion of my weight update that's uncorrelated with the gradient.
I thought the reason that is so if Ryan for t.
Oh yeah, if you have Brownian motion, that's going to be square root of t, and that's why I have this thing here.
Yeah.
Yeah, sure. It would have to be going in the same direction. I agree. Over this time interval t. But this is one time interval, and then in the next time interval, it could be going in a slightly different direction. Just temporarily or autocorrelated, right? Okay. Does that make sense?
Yeah. I was thinking.
Oh no. This is just one time. This is just one time interval.
Okay, so like maybe.
So in SGD we could, if we were thinking in an artificial intelligence context, where we're doing discrete weight updates, it would just be one weight update. I'm thinking. Yes. In the biological context, I'm thinking about this t as something that's smaller than the time delays in the feedback loop for learning that I have. This feedback loop here. So basically, what I'm trying to say, where am I? On this whole time interval from 0 to capital T, any information, any synaptic plasticity is not informed by information that came after time 0, only from. And there's always going to be such a T because there are just inherent delays. Yeah. Okay, cool. So I've made this kind of discrete analog way of representing continuous movement synapses. There's good bits and there's bad bits. And now I want to see how do the bad bits affect the learning rate. And it's going to be to do with the geometry of the error surface. So let's think about the local learning rate over this time interval. We're going to represent it by this k. And of course, this k will change at different time points. This is a local learning rate, temporally local. Now, I know that this, the left-hand side, has to be smaller than the right-hand side. My error has to be lower over time, which means that this k has to be positive. The more positive it is, the more I'm learning. If it's 0, then there was no learning. Okay? And all I'm going to do is just the second order Taylor expansion of k. And I get an equation that looks ugly, but is in principle. It's got a couple of components. First of all, this is the correlation of my weight update with the gradient. So this is the first order term in the Taylor expansion. So if I was doing true backpropagation, then this would actually be the gradient, and it would like.
Is this like the optimal learning rate? Or
no, I'm not specifying what the learning rate is. This is just, it could be anything.
Like I mean,
locally
just like so, I'm used to this just being a free parameter that we set our. So like.
Oh, sorry. Okay, you're thinking about learning rate in terms of how much I multiply the gradient by. I'm not talking about learning rate like that. I'm talking about something different. Sorry, that's what I'm talking about when I say learning rate is how fast the thing is learning.
Yeah.
I could be learning very fast even with small weight updates, or very slow with bigger weight updates. Yes. This is about how fast I'm learning, not about the magnitude of the weight updates. Yeah. So yeah, sorry, there's a confusion in terminology. It's not what you call learning rate normally in AI. Okay. So this is the learning rate equation, which is not learning rates in terms of how much moving. So I'm going to learn faster if I have a better anti-correlation to gradient. So if I can exactly get the gradient, it's going to be better. If I can exactly compute the gradient and go in exactly the opposite direction of the gradient, it's going to be better than if I can do half gradient, half noise. And that's reflected in this inner product. Right.
So what's the MSSW or omega?
Oh, this?
Yeah.
Oh, so this was my so if this was my this was this. This is my expression for learning over the time. The average movement. So I'm going to look at learning rates in turn over this time interval. And obviously, if that interpolated plasticity direction over the time interval correlates better with the gradient at time 0, I'm going to learn faster. And that's reflected in this term. So better anti-correlation to gradient speeds learning. If the norm of my gradient locally is larger, then I'm going to learn faster because, you can ski faster on a steep slope. So if I have a very strong gradient, I can learn fast. Whereas if I'm near a saddle point or a local, I can only learn slow. And then I have the second order term, which depends on the Hessian matrix, this. And I'm going to unpack this. But this is the curvature term. This is how much the inherent curvature of the error surface changes my learning rate. So mathematically, this bit is basically how much I project onto the Hessian matrix, and I'm going to give some geometric intuition. Suppose I had a completely linear error function locally. There was no curvature term, the Hessian was 0. In that case, this G would be 0, right? Because the Hessian is 0. Also, if I think about task irrelevant plasticity I was thinking about earlier, it's going to have no effect on expectation. I can deal with a huge amount of random movement. Why? Because I'm here. I'm here on a linear error circle. And I'm trying to go downhill. Suppose I only go in a direction that's very weakly correlated. It doesn't matter, I still go downhill. Suppose I have lots of random movement. Well, it's equally likely to go up the error surface as it is to go down the error surface. So I'm linear. So an expectation, task irrelevant plasticity, would have no effect on a linear error surface. I can think about an even better situation. Suppose my error surface is locally concave, I'm at a local maximum. In that case, if I move in a random direction, things are going to help me. That's going to improve my level of learning. Top of a hill, and you move in any direction, you're going downhill. Of course, these are not realistic situations. It's just for geometric intuition. More generically, if I'm a generic point in a generic area, either concave, convex, or linear, how much is task irrelevant plasticity? So moving in a random direction is going to hurt me. It basically equates to if I move in a random direction, on average, is that going to be upwardly curved or downwardly curved? The more upwardly curved a random direction is, the more the curvature is going to hurt my learning rate. And the more downwardly curved an average direction is, the more it's going to help my learning rate. And in fact, if I just did a weight update that is purely a task irrelevant plasticity, so if I literally did a brand new noise update, how much that would change my level of training is going to be proportional to the trace of the Hessian over n. So the average eigenvalue of the Hessian. Because a positive eigenvalue in the Hessian corresponds to an upwardly curved direction, and a negative eigenvalue corresponds to a downwardly curved direction. Okay, so we just did this Taylor expansion. Learning rule. I'm going to substitute my expression I had previously for synaptic plasticity over time interval, which I did in the first part of the talk, into this learning rate equation. So first of all, this bit is easy. I know how much this is going to correlate with my learning term. It's the amount of gradient information I have. So how big can this G be before my learning stops, the second orders? Because remember, there is higher order terms, which I'm going to ignore for now. I'm just looking at a quadratic approximation of the error. Well, G has to be, the smaller G is, the faster I learn, and learning stops completely when G outcompetes this gamma 1, so that the whole square bracket, everything in the square bracket is equal to 0. So when everything in the square bracket is equal to 0 is when this G, which I'm going to call local task difficulty, is equal to this blue equation here. And the smaller it is, the faster I'm going to learn, because the less the curvature hurts, the fact that I'm. So let's unpack this a bit. So first of all, in the numerator, we've got a gamma 1, which means if I have more movement in the direction of the gradient, the more gradient information I have, great, the better I am. The more bad curvature I can deal with. What about the denominator? Well, I've got a t here, which is saying that the longer I have to wait between weight updates, the less curvature I can deal with. Because if I have to wait ages and I'm moving, then even a small amount of curvature changes the gradient direction a lot over time period. And then in these big brackets, it's just basically the total magnitude of plasticity I have. And note that if I'm doing a Brownian, if I have some process that's affecting a Brownian motion, and I have a lot of synapses, so that's this gamma 3 term, then I might inevitably have a lot of plasticity that I can't. Cool, just to give you an idea, I trained a linear network, otherwise known as a and a non-linear network, so people on a student-teacher task, so generic task, as I showed you before. I did a noise-corrupted weight update in the style of this equation I had before. So I did my weight updates like this, so some amount of gradient and some amount of these noise sources. So the network's trained with some level of error, and they hit a steady-state error. And I also graphed this G. So this local task difficulty. And these dotted black lines signify the bound I just made here. So basically, when I'm initially, local task difficulty is very low. So essentially, it's almost like, so the average direction I go in is equally as likely to help me as to hurt me. Which makes sense, right? Because if I have a completely untrained network and I randomly perturb the weights, it's not going to on average change my error much. The more I train, the more that's no longer the case. Until tasky random plasticity hurts me so much that it cancels out any effect I have from having good gradient correlation with my phone. And in the linear case, the bound is exact. So I can a priori see how much local task difficulty I can cope with before I hit steady state error. In the nonlinear case, it's conservative in general. And this is something we found quite generically. And that's just because we have this higher order terms in the Taylor expansion that we haven't thought about. And in general, it seems numerically these seem to be bad for learning. But yeah, this is just to give a bit of insight or intuition into what's going on. So we keep training. Hi.
So now we're talking about like training machine. To adjust your learning rate or your gradient.
Then you can deal with that. So the only way to, so as you see, we have a t in this denominator, right? And the way adjusting your learning rate would be equivalent to decreasing. So the only way you can learn further is to basically weight update. That's what's reflected here. But in AI, you can, I mean, to prove convergence of any algorithm, in the end, you need to have weight updates whose learning rates, in your sense of the word, scales to 0, right? Whereas in the brain, you have unavoidable lower bound in the plasticity magnitude. Synapses move. But yes, I agree that you can deal with noisy weight updates by changing how fast you're moving in weight space to 0.
And when you're doing that in this model, that's going to reduce the amount of noise.
No, it's gonna preserve the amount of noise. Everything is going to be smaller. Well, okay. So if we go back to our weight update here. So if I change suppose I was doing noisy gradient approximation. If I wanted to scale how much I was moving in each time step, I'd want to decrease gamma 1, but I'd also have to decrease gamma 2. So both of these two terms would be multiplied by a constant. Gamma 3 is what I'm thinking of as Brownian motion in the synapse. That's something that's unavoidable, going from other things.
So
Yeah, you can't. There's some level of Brownian motion in the synapses you can't get rid of.
Yeah, but so like if it represents time here, then if you were shrinking the time interval, that would also reduce.
That's another way of doing it. I agree. That's equivalent. So, but of course, if we're looking at a very, very small time interval, the Brownian motion is growing with root t, whereas the learning rate update is growing with t. So the relative proportions of those two things is going to change as I shrink the time interval. Way there's this root t here. Wait, where was I? Yeah, I was here. Okay. Good. Anyway, so I had this formula, well, the formula we were just looking at, which is generically looking at decomposing synaptic plasticity into good and bad plasticities. And I'm going to substitute it into this local task difficulty thing that I made up. I'm going to decompose local task difficulty into task relevant contribution and a task irrelevant contribution. So as we said before, task irrelevant plasticity, so something which doesn't have information on the loss function, is going to project equally on average onto the different eigenvectors of the Hessian matrix of the loss, because it's not constructed with respect to loss. It has no information on loss. It can't bias towards different particular eigenvectors on average. What that means is that how much it affects local task difficulty is going to depend on the trace of the Hessian. If I have a very high positive trace, as I was saying earlier, then most directions are very upwardly curved. So task relevant plasticity. So that plasticity is going to hurt my learning rate a lot. Okay. Because yeah, I'm going to be deflected upwards on the error landscape. And then there's the contribution to my task relevant plasticity term. So even if I was doing pure gradient descent, like back propagation, as you were saying, I have to scale my learning rate if I want to converge. Because as I get closer to a local minimum or a saddle point or whatever, the direction of steepest descent is always going to also be in a direction of non-zero curvature. And as my gradient becomes close to zero in magnitude, as I approach a stationary point, my curvature doesn't do that. So in the end, what happens is the positive learning benefit I get from going down the gradient is more than cancelled out by positive curvature. By the fact that, for instance, around the local minimum, my error function is locally convex, which is why I have to shrink my learning rate as I approach. Wait, do you have a question? Oh, great. Okay. This term is representing that. It's basically how much does the gradient, the normalized gradient, project onto my onto the Hessian. Now, I've been using a first order learning rule. If I wanted to generalize this to second order learning rules at the cost of complicated equations, this would be smaller, because in the end, second order learning rules like ADAGRAD or whatever, what they do is they bias your direction of plasticity towards flatter directions, and flatter directions are good because the gradient stays more constant along them. If I was using that kind of learning rule, then this would be smaller, but I'm not. Okay, now I'm going to get to the core bit, which is I've looked at the second order Taylor expansion of how fast I'm learning, and I've decomposed it into a benefit I get from going down the slope versus a cost I have by the fact that on average directions are upwardly curved the more trained I get. Saying that if I randomly perturb my weights, my error goes up the more trained I am. Now I'm going to look at, I've related all this to the local geometry of the error function. Now what I'm going to do is do a mapping, look from a particular network, an arbitrary network at an arbitrary weight vector, an arbitrary state. I'm going to map it to a different neural network, and that mapping is going to change the geometry of the error function. And that's going to change how much curvature I have in average direction, and therefore change my learning rate. And the point is that basically by adding redundancy in the case I'm doing, but maybe other architectural modifications in the general case, I can increase my robustness to task irrelevant plasticity. And by manipulating my network architecture, I can end up with networks that can learn to good steady state error, even in the presence of high amounts of noise and lower bound the magnitude of synaptic plasticity. Okay, I guess I pretty much said this late, which is how do I re-engineer a learning system to learn well despite a bad learning rule with lots? In the context of this talk, one way of approaching this is re-engineering the system to have high robustness to task irrelevant plasticity while maintaining sensitivity to task relevant plasticity. Okay, so I'm going to take a neural network with the state W. I'm going to make a family of mappings phi. In my particular case, these are going to be mappings that increase the number of neurons, but it wouldn't necessarily have to be that. But the key thing about this mapping is it's going to preserve the input-output properties of the network. So I'm going to have a bigger network that it saves exactly the same as my original network at the state W. So the error is the same. F dash being the error of this neural network, and F being the error of this neural network. Now, I'm going to, given values for the gradient and the Hessian, I can just propagate them through phi by using the chain rule to see how the gradient and the Hessian of this guy look. And from that, I can see how the local task difficulty, that thing I constructed, changes. And I can, in fact, minimize it in n, the number of synapses, because what I'm going to be doing is looking at families of mappings that change network size, for instance, adding neurons. And I can find an optimal network size, essentially, in particular cases, so all the ones I look at. So I think this could be a generic analysis template for various architectural modifications. I've just looked at 2 here. So just to recall, what the context we're in is we're making a generic kind of random task, let's say, where there's a teacher which has random fixed weights and families of students. The students have to learn to be the teacher to recreate the input-output properties of the teacher. And the way they do that is by supervised learning. We put in inputs to both the teacher and the student, and then the teacher outputs become the labels of the student, and then we do noise-corrupted supervised learning of the student. And we're going to have a family of students. And just like at the beginning of the talk, the key thing is that all of the students can theoretically learn the teacher to 0 steady-state error. So, yeah. So generally, the teacher is going to have the same architecture as the smallest student. Okay, I'm going to start with a really simple example, just to give insight. A linear network, so a matrix. So the output of my student is Y, the input of my student is U, and I just put it through a matrix, push it through a matrix W. There's an immediate problem here, because if I change the dimension of my matrix W, I change the number of inputs and outputs, which means I can't have a fixed teacher. But the way around that is instead I just project the same teacher, the same input output mapping into a higher dimensional space. And I'll give a bit more insight into that. So basically, let U and Y star U be the inputs and optimal outputs generated by the teacher. I get some semi-orthogonal matrices D and B, which basically go from a smaller dimension to a higher dimension. And I project the inputs into the higher dimensions and the outputs into higher dimensions via these matrices D and D. So essentially, for my larger students, they're going to be learning the same input-output mapping up to an invertible transformation, but embedded in a higher dimensional space. So these might be this U and this Y star U might be low dimensional. These guys are still low dimensional, they're just low dimensional objects in a high dimension. It's the same task. Hi.
So
Y star is the optimal output for a given input, the teacher generated output.
I'm going to take that same input you can project it into some
Higher dimensional space, higher constant matrix D.
And then you can use a different model to predict Y star.
No. I have the same model to predict Y star from U. I just project that Y star U into a higher dimensional space. In fact, that should not be a D, that should just be Y star U. My apologies.
Oh, okay.
Sorry, that's a mistake, I realize now. So that should be D of Y star U. So this is an invertible transformation. If I know what B and D is, then given these two guys, I can infer these and vice versa. It's an invertible transformation. So it's the same task, just embedded in a higher dimensional space. I'm going to define how much change by these parameters C1 and C2. C1 is the proportion by which I increase my number of inputs, and C2 is going to be the proportion by which I increase my number of outputs. And they're going to be greater than 1. I'm only going to be increasing network size. Note that the number of weights from the expanded network is going to be C1 times C10, which is now I'm going to, given an arbitrary fixed state W of the smallest, I'm going to project the state via this transformation phi in such a way that the error of the larger student under the image of the projection is the same as the error of the original student, which had weights W. So it's going to be this mapping. And you can see that because of these identities here, essentially, if I multiply this new projected input by the PT, that cancels out, and the same with the D. So the larger student network is going to have exactly the same error as the smaller student network. Right.
Still have to be.
Yeah, sorry, this should not be a D. That's a mistake. Just ignore this D for the rest of the time. Yeah.
And
Sorry, I didn't hear what you said.
you have B, U on the bottom, right?
Yes.
And then above the line above it, B plus U.
There shouldn't be a U here. Sorry, I'm very sorry. There shouldn't be a U here. So basically the B, yeah, so there should be a B here as well. Because it's taking, sorry. This input should be BU instead of B here, instead of U here, which means that I have a BTB, which is the identity.
Oh.
And it cancels out. Sorry, this equation has a mistake.
Oh, okay, yeah. Okay.
You see what I mean there? Sorry. Yeah. Okay. Now, how does my local learning rate, how fast I'm learning, change under this mapping? So for given proportions of task relevant to task irrelevant plasticity, does the smaller network learn faster or does the larger network learn faster? Well, to answer that question, I'm just going to basically put in my expression for interpolated synaptic plasticity, which we did which we got in the first part of the talk, into the second order Taylor expansion for how fast I'm learning. As before, the first order term is just how much gradient I've got in my weight update. And it remains to see how this local task difficulty changes under phi. So because it's a linear example, I can calculate everything analytically. And I can say that under the image of the transformation, the norm of the gradient doesn't change. Whereas the trace increases by a factor C2, the number of outputs. Okay. Okay, so the expected value of the local task difficulty is going to be, well, this is what we had before. This is exactly what we had before. And we can put in these changes and see how the expected value of the local changes. And this guy is going to get an extra C2. So this is basically how much. So if you remember, this G1 was how much curvature there was in the direction of the gradient. So if I'm going down the gradient, how much is the inherent curvature of the surface deflecting me upwards? Well, that's going to increase by a factor proportional to how much it increases. Because the trace also multiplies by a factor C2, I'm going to have to put an extra C2 here. But then this n is the number of weights, and the new number of weights is C1 times C2 times n. So this decreases. So we can see that by manipulating C1 and C2, we can actually change this expression. Hi.
Just remember, C2 was the input dimension.
Output. How much we're changing the output dimension. So if I've doubled the output dimension, C2 is 2. In this term, basically because I did the maths and it worked out like that. But basically, this is the maybe for easy insight. This is the first term for the untransformed, right? The gradient is staying the same in magnitude, whereas this is increasing by a factor. So you can see why overall this would probably increase by a factor C2. Yeah, good.
What's going to C2 there? Sure.
Yeah, I guess it's, yeah. How the maths works out, I guess, yeah. Okay, now what I want to do is I want to minimize, so just for a proof of principle, what I'm going to do is I'm going to fix the ratio. There's no reason for this except to demonstrate, it allows me to do some numerical tests of all the maths I've done. Because if I fix C2 over C1, then I only have one free parameter in this equation, because C1 depends on C2 and vice versa. So now I can minimize in C2, or equivalently in C1, this expression. And I'm going to say that this is going to minimize the steady state error of the network. Why? Because suppose I'm in my original network, and I've learned, and I'm now at a weight state that's a steady state error. Steady state error is when any positive contribution learning from the first order term cancelled out by the curvature term. But now if I transport the network to via this image mapping phi in such a way that this g decreases, then suddenly this term is smaller, this red term is smaller, which means learning rate is again positive and I can learn a bit more. So I do that minimization. I just take, d by dc1 equals 0, or d by dn equals 0, and take the stationary points, and I get this formula for the optimal network size. One assumption I have to make to get rid of the annoying trace terms and stuff, but one which we numerically seem to be fine when we looked at it, is that essentially the gradient projects evenly an average onto the different eigenvectors of the Hessian. Which is this gray thing, which is equivalent to this gray equation. So let's look at this graph then. What's happening? So if you remember, gamma was the different proportions of different kinds of plasticity. So the first term of gamma was the amount of task-relevant plasticity. The second term of gamma was the amount of systemic gradient approximation area you could think of. Yeah, right. And then the third term was the amount of Brownian motion. And the analytic, this analytic equation we got seems to conform well to the numerical results. Because indeed, the steady state error, as we change network size, the best network size seems to well conform to the analytic errors. Okay.
I just think about this assumption. Yes, it doesn't seem useful to me, like when I'm thinking about neural net, like the steady state is presumably going to be like fairly close to a local minimum. That means that the gradient is going to be pointing in a direction where the Hessian has but it's like pointing towards the bottom of the bowl, right? So
it's always going to point in the direction of the positive curvature, right?
Yeah.
But also, okay, well, also when you're in that situation, you know that locally around your minimum, you're going to be convex. So every single direction is the direction of positive curvature. There's no non-positive direction of curvature near a local minimum. But yeah, to give a bit more intuition, and I first of all, in the linear case, I think it's reasonable. And the reason I think it's reasonable is because in the linear case, the Hessian is constant, whereas the gradient is moving around all over the place. So the Hessian stays the same the whole thing. So in this case, it's reasonable. I'll go to a nonlinear case where actually I will agree with you, it might be less reasonable. And the only way you can really test it is numerically. I had some kind of, okay, I'll get to it later. But in this case, the Hessian is constant. Okay, anyway, so this is really just a proof of principle to show that, okay, first of all, what we're saying is that by changing the network size, we can change the steady state error for a given proportions of task relevant to task irrelevant.
So another question was like, this slide looked like it wasn't about the network size, right? It was about C1 and C2, or possibly also the ratio. Like,
C1 and C2 are directly affecting network size.
Yeah, but what I'm saying have the same size of network values as C1.
Agree, and I'm going to get to that next slide. Because yes, if you go to the previous slide, actually increasing C1 seems to be much better than increasing C2 because C1 is only in the denominator and it's only going to decrease this, whereas C2 is going to increase this. Yeah. But the only reason I fixed that was just to have one free parameter in order that, because if I only increase C1, the optimal network size would be infinity. And it's just a demonstration of the maths, that the maths checks out. Nothing more than that. But actually, yes, you kind of preempted my next slide. We previously fixed this ratio. What if we instead just fix C2, given the fact that increasing C2 seems to be bad and increasing C1 seems to be good? Well, then the bigger we get, the better steady-state error we get. And so a line of work we're doing now is thinking about, does this explain any architectural features in the brain? So I guess, yeah, so you guys don't necessarily all have much neuroscience backgrounds, but are you familiar with the cerebellum? The cerebellum has an interesting architectural feature. So it has this kind of cell. So the cerebellum is just a tiny bit of brain right here. It's not much. It doesn't almost look like your brain if you look at an image. Nevertheless, there's one kind of cell in the cerebellum called the granule cell, which consists of 70% of the neurons in your brain. It's got about 50 billion granule cells in the cerebellum, and your brain has about 85 billion neurons. And the architecture is that a small number of inputs to the cerebellum project into this massive high-dimensional space of granule cells. So the granule cells are having a high-dimensional representation of a fundamentally low-dimensional input. And the weights of these large granule cells are adapting due to, basically, you get an error signal from something called the mossy fiber. Sorry, the climbing fiber, not the mossy fiber, which is very low dimensional. Okay, sorry, I think I didn't realize that people are not so much into neuroscience here. But basically, the point is that we know that this kind of learning system is necessarily going to be only give you a very bad approximation of gradient because the feedback is very low dimensional. So maybe the reason we have all these like billions and billions of granule cells basically have a really high input dimension to allow us to actually learn fast despite huge amounts of task irrelevant plastic issues with gradient approximation. That's a bit of a tangent. That's something we're working on now, but just. Hi.
Can I ask what these cells do with granulars? Yeah.
So yeah, okay. Is there a broad I could? Okay, basically the cerebellum. Not really sure exactly everything. It does lots of stuff like control of motor movements.
Yeah.
You have lots of interesting pathologies when you have a bad cerebellum. For instance, if I try and touch my nose, but I have a damaged cerebellum, I'll go here. I might have some relations. If I do the knee-jerk reflex, if I have a damaged cerebellum, instead of jerking and going back, I do relations. Inputs to the cerebellum come from a small number of neurons called mossy fibers. And each mossy fiber connects with billions of these granule cells. So there's a dense layer of these 50 billion granule cells, over half the neurons in your brain. But because they're getting inputs from a low-dimensional set of neurons, and I'm assuming that what they're encoding is quite low-dimensional, because that's the only thing they get inputs from. And then they're also projecting their outputs onto something very low-dimensional. So it's like there's this massive dimensionality expansion. You could think of it as a massive hidden layer with low-dimensional layers to the bits before and after. Okay, so nonlinear example. Now I'm going to look still at simple neural networks. So I can do the maths. Feed-forward neural network. Feed-forward neural networks with hidden layers and sigmoidal nonlinearity. Just for the sake of an example. Unlike in the linear case, I can increase the size of the network without changing the number of inputs and outputs. So I can have a fixed teacher. I don't have to do all that stuff with projecting the teachers that was before. And my mapping is essentially just going to add ghost neurons, or neurons connected by ghost synapses. So I'm going to add neurons, but they're not great. The synaptic connectivity is 0, so they don't actually affect the output of the network. But of course, as soon as I perturb the new weights by which the new neuron is connected, then the output does change. Hi.
The output has to be 0. The input is 0.
No. All the weights are non-zero in the left. Yes.
The output has to be 0. But the input.
Yeah, sure. I just chose one where there was 0. It doesn't matter. Basically, any mapping which preserves this is going to be fine. Okay, so there's no issues compared to the linear example. First of all, we can't analytically look at calculated derivatives like we did before in the linear example. But we're going to be able to bypass that. But another limitation is, in the linear case, there was always an invertible mapping between smaller and larger networks. There are always equivalent states with equivalent errors. In the nonlinear case, what's actually going to happen is that larger neural networks can exhibit a fundamentally wider range of behaviors. There's going to be behaviors in the larger neural network which can't be replicated by the smaller neural network. My analysis is going to be looking at weights in the image of some mapping from the smaller neural network. So in that sense, I'm looking at a restricted set of weights. I'm going to talk about the implications of that later. Okay, so as before, I'm going to pick an arbitrary weight vector of state neural network state W. And as I said, my transformation is going to just add 0 weight, so it's going to add a neuron with ghost synapses. And now if I think about a representation of this mapping, it's either going to send, if I take a weight here, it's going to basically be the identity transformation on the existing weights. So it's going to be a 1, or it's going to add a new 0. So if I picture this as a matrix, if I picture this mapping as a matrix, the matrix is going to be like an identity with a couple of zeros in it. So it's going to be a semi-orthogonal matrix. It's going to satisfy this property. And now, whatever my W was, whatever the state of the neural network that I chose, this A is going to be fixed. Just by the chain rule, I get these identities. So, well, I guess these are clear. So basically, A transpose times the new gradient is equals the old gradient, and A transpose times the new Hessian times A is the old one. That should be a Hessian, sorry. There should be a 2 there. So that's just the chain rule. And now the assumption I'm going to make is that because A is fixed, because A has nothing to do with the weight state I was on, it's going to have nothing to do in average with the gradient direction or the Hessian direction. So basically, the gradient is going to project unbiasedly onto the different eigenvectors of A. And similarly, that's the only one. Okay. So basically, the gradient is not going to be biased towards a particular eigenvector. I think this is reasonable. A is fixed, whereas W could be anything, the task could be anything. If that's true, then essentially, when I do this projection, some of the basically, I can think about how much it's going to take the norm of these two. This has some 1 eigenvalues and has some 0 eigenvalues. And the norm of this is going to depend on how many 0 and 1 eigenvalues. So I get these approximations. I say that the gradient is going to expand by roots the ratio by which I've increased the number of weights. And the trace is going to increase linearly with the number of weights. So if that assumption is true, then these are exact. But of course, it's never going to be exactly true because there's always going to be fluctuations, like there's going to be a slightly higher projection onto 1 eigenvector. So, well, given these, I can now substitute these things into the local task difficulty like I did before. So I had my new expression for the local task difficulty is now as a function of the old components of the local task difficulty of the untransformed mapping. I'm going to be adding these terms, extra terms. So as I get, again, I'm going to make the same assumption that you questioned earlier. And in this case, I actually agree that it's a less valid assumption. So it's the assumption that I get the gradient projects unbiasedly on average onto the eigenvectors of the Hessian. I did put I have a long thing in the supplementary information of the paper giving a bit more insight into why. It's a heuristic. The lucky thing is that even if it's not very true, it doesn't in the end affect the optimal network size calculation. We also did some other simulations of a very asymmetric task, classification task, and checked it out, and it seems to be fine. But of course, I'm never going to say that in a generic sense. It's never always going to be. It might not always be true. It just seems to have been true when we tested it. And even if it's not true, it doesn't in the end affect our optimal network size calculation. But anyway, under this assumption, we get a formula for optimal network size again. And actually, what I forgot to do last time, but I'll make up for by doing this time, is unpicking this a bit. So if you remember, gamma 1 represents the amount of movement in the direction of the gradient. Gamma 2 represented a systematic gradient approximation error term, due to e.g. the fact that I can only correlate to some fixed degree with the gradient because I have, say, a bad learning mode. And gamma 3 was like the amount of Brownian motion. It's something, sources of synaptic plasticity that increase with network size. So of course, if I have large amounts of task relevant terms that increase with network size, like a big network synapse of Brownian motion, then that's going to penalize excessively large networks. You can see this as gamma 3 squared in the denominator. On the other hand, the fact that I'm flattening out the error surface essentially as I get bigger means that if I have a fixed proportion of, if I have some task relevant plasticity terms that are fixed in relation to how much gradient information I have, so I'm saying like 10% gradient, 90% noise, as I have with the gamma 2, then larger networks do better because flatter error surface. If I have a bigger time delay, same difference. Bigger networks do better with a bigger time delay because they have a flatter error surface. So the gradient changes less over a longer time interval. And n here is the size of the teacher network. If I have a bigger teacher, I need a slightly larger optimal network size.
What's the n star?
N star is the optimal network size.
Yes, on the right hand side.
Oh well, I could have rearranged it to the n star equals but the equation. Yeah, basically. In fact, I can show you the rearrange. It's just an easier equation. And then I did some numerical simulations again, like I did in the last case, and again they seem important. But in general, I think I was looking at small, easy neural networks, like tiny compared to the ones used for artificial intelligence applications. And I think in general, if I looked at really large convnets or whatever, or basically large systems of large neural networks, I think in general these would underestimate. And the reason is a limitation I alluded to at the beginning, which is the fact that I'm only looking at network states of the transformed network in the image of states of the original network. If I add a lot of layers to my network, maybe that opens up whole new areas of weight states which are not isomorphic, which I can't transform back to the smaller network. And maybe those have very low local task difficulty. Maybe I open up new, really nice flat directions of my space. But that's an advantage of larger neural networks that I kind of attribute to the larger range of input-output behaviors that they can kind of well known. Like larger neural networks have larger sets of behaviors, means the best one is better. This is purely due to the local geometry of the error surface flattening out. So really, it's not like I find these particular n stars of any real importance. They're just making sure the maths checks out. But really, the point I want to make here is that transforming neural network architectures can make you more robust to task irrelevant plasticity. And that could be in an artificial intelligence application due to other things like, I don't know, like having a stochastic gradient, of course, or just having bad noisy labels, noisy inputs or labels, that kind of stuff. Different architectures of neural network have different robust task relevant plasticity, and that depends on the local geometry of the network. That's really the fundamental message I want to give here. And that pretty much concludes the talk. So I think I've gone through everything now. Yeah, thank you very much for listening. Papers in the fire archive should be published. Thank you. Yeah.
How would you feel about timing? You mentioned that you only have a